should be rational numbers. And now we are going to give examples of two ideals. I mean a left ideal and a right ideal. Let I be this set where A and B are rational. By this Q we mean the system of rational numbers, or rather the set of rational numbers. Let this be one thing and J be the set of all matrices where the second column is 0. In J we consider all matrices where the second rows are 0. Right. Okay. So now you have to prove that I is a left ideal and J is a right ideal. I am not going to write that here, although I will quickly show that that is the case. What do we need to show that I is a left ideal? First of all, we need to prove that both I and J are subgroups of R under addition, and that thing can be done rather quickly. You take any two elements in I, they look like this. This is one element and this is say another element, where A1, A2, B1, B2 these are rational numbers, and you take their difference, so that becomes A1 minus A2, B1 minus B2. These are also rational numbers, and this matrix also has the same form as the other matrices in I, so that means it belongs to I. Okay. Similarly, you can show that, so that means I is a subgroup of R under addition. Excuse me. And the same thing you can do with J. You can also similarly show that J is a subgroup of R under addition. So that thing is okay, fine. Now what happens when we multiply any element of I by an arbitrary ring element from the left hand side? You see, if I take an arbitrary ring element alpha, beta, gamma, delta say, and I multiply this element of I by this element from the left hand side, what do I get? Alpha A plus beta B. Alpha times 0 plus beta times 0, that means 0. Gamma A plus delta B, and then 0. So you see that since these are rational numbers, all the alpha, beta, gamma, delta, A, B, these are all rational. So these two are also rational. And this matrix again has the same form. So this belongs to I. So multiplying any element of I by an arbitrary ring element from the left hand side lands us inside I. So that means that tells us that I is a left ideal. Similarly, if we multiply, let us just see that one also. Multiply an arbitrary element of J by an arbitrary element of the ring, but from the right hand side now. So this gives us A alpha plus B gamma, A beta plus B delta, and then these two will be 0. So this again has the form for it to be in J. So this belongs to J. So I is a left ideal and J is a right ideal. And I will just mention that here. it can be verified that I is a left ideal and J is a right ideal of R. Now what happens to their intersection? Let us see. Note that if we take a matrix, say alpha, beta, gamma, delta, belonging to I intersection J, it belongs to both I and J, then this matrix has to be like this. So that means beta and delta have to be zero. At the same time, this matrix has to also be like this. That means delta and gamma have to be equal to 0. So beta, delta and gamma, they must be 0. Then beta, delta and gamma, these are 0. Hence, I intersection J looks like this. It consists of all matrices where only the first row, first column entry is possibly non-zero. Okay, this A can be 0 also, but it can be non-zero. So the others are fixed and they are 0. Right. Now, note that neither of the following two matrices belongs to I intersection J. And what are they? 1 1 1 1 1 0 0 0. What do we get when we multiply these two? 1 plus 0 1, 0 plus 0 0, 1 plus 0 1, 0 plus 0 0. This is one matrix, and the other matrix is just the same product. I mean, not the same product, but it involves the same factors but in the opposite order. One plus 0 1, 1 plus 0 1, and then 0, of course. Okay, so what we are saying here is this: I intersection J is an additive subgroup. There is no doubt about that, because I and J are subgroups of R under addition. But if we take this element from I intersection J, it belongs to I intersection J because these elements are 0. So it has the form to be in I intersection J. If I multiply this element from the left hand side by an arbitrary ring element, the result is not in I intersection J because this is not 0. At the same time, if I multiply this element from the right by an arbitrary ring element, which is actually not arbitrary but nevertheless this is an element, that result is also not in I intersection J. This tells us that I intersection J is not a left ideal, and this tells us that I intersection J is not a right ideal. So this is an example where we have an intersection of a left ideal and a right ideal, but the result is neither a left ideal nor a right ideal. So no question of the intersection being an ideal. Okay, so that is our conclusion. So we can't say anything about such an intersection. So thus I intersection J is neither a left ideal nor a right ideal. And as such not an ideal. So that's what we can say about the intersection of a left and a right ideal, that we can't really say anything in general. Right, now after that we have exercise 18 or 17, sorry. If R is a ring and A is an element in R, let RA, again we are going to, it's that type of exercise. We are going to define a subset, then we will be asked to show that it is a left or a right ideal, things like that. It is the set of those elements in the ring such that if you multiply A by such an element from the right you get 0. What do we have to show? Prove that RA is a right ideal of R. So this is quick. RA, the first thing you see that RA contains the 0 element. If you take 0 in place of X, what do you get? Definitely 0. So that means 0 is in RA. So RA is a non-empty subset of R. So next we show that RA is a subgroup of R under addition. Let X and Y be two elements in RA, and simultaneously let us also take a ring element to verify the second condition. Then since X and Y belong to RA, so AX and AY are both 0, and hence AX minus A, or A times X minus Y, okay, this will be AX minus AY, which is 0 minus 0 is equal to 0. So that means if I multiply A from the right by X minus Y, that product is also 0, and as such X minus Y belongs to RA. Thus X minus Y belongs to RA. This shows RA is a subgroup of R under addition. next, okay, now we have to show that RA is the right ideal. So that means this arbitrary element of RA, we have to multiply it from the right by a ring element that we have taken. So XR. Next, if we multiply A by XR from the right hand side, what do we get? Because of associativity of multiplication, I can write it as AXR. But AX is 0, so that means 0R, and you already know that in a ring 0 times anything is again 0. Hence, so now XR will be in RA because this product is 0. So we have multiplied this element X in RA from the right side by an arbitrary ring element, and the product is in RA. So RA is an ideal, not ideal, a right ideal. So RA is a right ideal of R. Okay, so that completes the solution. After that, there is one more. Exercise 18. If R is a ring and L is a left ideal of R, let lambda L, it's a symbol, lambda L, again we are going to define a set. It's the set of those elements in the ring such that XA is equal to 0. Note the difference, that one was AX, but this is XA is equal to 0. But what A? Now we haven't chosen any A here. That here we already chose an element A which was fixed. Now we don't have any A, but we are going to vary this A over the left ideal L for all A belonging to L. Prove that lambda L is a, oh, this is two-sided ideal now, is a two-sided ideal of R. So you can see that if we are given a left ideal, then we can generate a two-sided ideal from that left ideal in this way. Okay, so the first thing is, of course, excuse me, I should not step on this wire, there is wire. Okay, so the first thing we should see here is that lambda L contains the 0 element. Can we take 0 here? If I take 0 in place of X, is it true that 0A is equal to 0 for all A belonging to L? Yes, it is true. In fact, this is not just true for all elements of L, but for all elements in the entire ring. So all the more so it is true for elements of L. This tells me that 0 belongs to lambda L, and hence lambda L is non-empty. we can mention that, in fact, note that instead of not writing anything all the time, let us just mention it once. 0 belongs to lambda L, and hence lambda L is a non-empty subset of R. Now next, let x and y belong to lambda L. Then xa is equal to 0 and ya is also equal to 0 for all a belonging to L. That's the condition for being in L. Oh, sorry, I mean for being in lambda L. Okay, so now x minus y is equal to xa minus ya 0 minus 0 for all a belonging to L, right? Hence x minus y belongs to lambda L. So lambda L is an additive subgroup of R. Is a subgroup of R under addition. So next we have to show that lambda L is a two-sided ideal. This, however, we cannot do at once. I mean, by taking an element of R and then multiplying an element of lambda L by that R from both sides. I mean, we can do, I mean, we will have to do, but we will do it one after another. The first, which one is the easier one? So if I take, anyway, let's just go through it. Next, let R be any element in R. Suppose we are trying to show that XR belongs to lambda L. For that, what do we need? We need to show that XR A, okay, this will be the difficult one. So let us first say that Rx belongs to lambda L. Then Rxa, okay, Rxa can be written like this: R times Xa, and this is equal to R0 equal to 0 for all a belonging to L. Why? Because Xa equals 0 for all a belonging to L, that's why. This implies Rx belongs to lambda L. Next, what happens when we take XR? Okay, XR is equal to XRA is equal to X times RA. This is also equal to 0 for all A belonging to L. But why? because Ra belongs to L for all A belonging to L. And why is that true? Okay, what are we doing here? See, we have taken xr and we are multiplying that by A, or rather we are multiplying A by xr from the left hand side. That can be written like this, x times Ra. And we are saying that this is equal to 0 for all A belonging to L. What is the condition? The condition is that if I multiply x from the right side by any element of this left ideal, then I get 0. Ra itself is an element in the left ideal. Why? Because you see, A is in the left ideal and R is an arbitrary ring element. So if I multiply A from the left by R, Ra is again in L. So now in place of this A, you think of Ra. Because this A is not a fixed A, it's any element in L. In particular, for this element Ra in L, x times Ra will also be equal to 0. Okay. So that means multiplying A from the left by xr has got me 0. So according to the definition of lambda L, xr will belong to lambda L. Hence, xr belongs to lambda L. This shows lambda L is a two-sided ideal. Although we decided to not mention the words two-sided, but here we are mentioning just to emphasize the fact that L is left but lambda L is two-sided. So from a left ideal we can get a two-sided ideal, and this completes the solution. Okay, then again a slightly difficult exercise, and its nature is also different. It's somewhat different than what we have been doing for some time. This is exercise 19, and there is an asterisk. Let R be a ring in which the cube of element is the element itself for every x belonging to R. This condition is given. Prove that R is a commutative ring. Okay. So the solution goes like this. It's difficult to say how one comes up with such a solution, but you just have to play around with the symbols, and eventually, if you are lucky, you will get the solution. So it's just like that. Trial and error for many days, many months, and then eventually you come across a solution. So I'm just going to copy whatever is I have written here. For x belonging to R, we have, okay, now we are going to use this condition on not x but something else, x plus x. So x plus x whole cube is also equal to x plus x. Now let us just expand this and see what we get. On the left hand side we get something like this. On the right hand side we have this. So if we multiply the terms out, we get x square plus x square okay. So then after that again if we multiply, what do we get? X cube plus x cube plus again x cube plus x cube plus x cube plus x cube equal to x plus x. But we already know that cube is equal to element itself. So that means here we have 8 x's and here we have 2 x's, and you can use cancellation law which is available for us. Because why? Okay, you have to keep in mind the before doing anything you have to be sure why what you are doing is actually justified. Since we are in an abelian group and in a group cancellation laws are available, that's why we can do it. We can cancel, say, this from both sides. So assuming of course there is 0, that gives us what? 6x is equal to 0. And we are not going to show this. We have seen this calculation. From this we get 6x equal to 0. So we are just simply going to write this, which implies six x is equal to 0. Similarly, in place of x plus x, now if we take x square minus x, its cube is also equal to itself, and if you expand and do all the calculations, you will get this. This gives 3x square is equal to 3x. I want you to actually carry out the calculations and see that you get this. Okay. Now next, one can verify that this subset 3R, and what is the meaning of 3R? It is 3R where R varies over the ring. What do we mean by 3R? See, we have already said in one exercise, in the first set of exercises, what 3R means. 3R in the ring is R plus R plus R. You remember that exercise which asks you to show MA times NB is equal to MNAB. There itself we have the definition of, actually we don't have the definition of MA there, but there we discussed that MA actually comes from group theory. So in the additive group of the ring, this R plus R is nothing but R cube in general group theory. But since the operation is addition, so instead of R operation R, we have R plus R, and that we are writing as 3R, right? So with this understanding, we understand what the set 3R means. But one can verify that this is a subring of R. Now this is something we haven't said yet. What is a subring? A subring is a subset of some more ink. I can't put too much ink at once. That will create a mess. That's the problem. Okay, it was slipping out of my hand. Averted a very big mess up just now. Only got some on my hand, and it doesn't matter. So a subring is a subset of the original ring that is itself a ring when we restrict the operations in the original ring to the subset. So for example, if you think of the ring of rational numbers, there is the set of rational numbers, you have addition of rational numbers and multiplication, and you think of the subset z of integers.